So that presentation we had 2 days ago on solar panels, probably a week early for what we needed it, because we're going to get into electrostatics, and then we're going to get into Ohm's law and electricity within the next 2 weeks. So it would have been nice to have it at the end of the next 2 weeks. But the lab itself is going to be, he's provided us with 2 labs that are based on that solar panel. We will bring the solar panel up. We will do some wire connecting after we've got all of the basics done. And then we have a couple, 2 or 3 days of experimental stuff that we're going to work with at the end of the electricity unit. So unfortunately, this was the time that he could come up here, and that's just the way it was. But it was still a good enough presentation. There were some interesting aspects to it, talking about solar panels and what's the benefit of them, all right? And where do you see you using the solar panels? Okay, has anybody seen anybody with solar panel usage?
We always have it like this day, like John Bailey, they run all their stuff on the farm across it, all on solar panels.
All on solar panels?
Yeah.
Oh, really? Off the grid or on the grid?
I think it's on the grid, but it's all basically their home section, just all solar panels.
Okay.
We have solar panels so that are placed to
For the water bowls, so that keeps the heater going? Yeah. Electric fence uses them?
Campers.
Campers? Yeah, starting to see more of those. Those aren't as effective because usually we cap in trees, so they're, but I have seen them out at camping for sure. Anybody else?
Lionel Jason's got a bunch.
Yeah, what does he use them for?
Just to power the house.
House power?
Yeah.
Anybody else? Yeah.
Jake Doobie had one on his S10.
S10. What?
I don't know. I figure you're having sleep bar.
Oh, jeez. Right. I've seen them. I've seen lots of guys. A number of fish shacks. Yeah. So you use your light, power the battery, and then use your light off of it.
Keeps the battery
charged. Yeah. So we can see it happening. The one thing you need money up front with those. Like he said, it's probably about $25,000 to set up a whole home system where it would take you 15 years to see the benefit for it. Now the good news is they have 25-year warranty on the actual panels themselves, but 15 years is a long time for that investment to start making, you saving money where you're not spending any more money on power. So until they can effectively make those solar panels worth a lot less money, I think it's gonna take a while to see what happens. All right. So as we get going into it, as we get into capacitors today, we'll talk about what he talked about, the panels on the solar, where he said that, so you have a block of panels, right? And he talked about the one section. So there was 2 little guys here, and then the big squares in the middle of that panel. And basically what he said was this stored positive charges, this stored negative charges on it. And then basically what happened was when the sun hit it, it provided electrons to it. So then that's what creates the flow of electrons within it. So in order for us to really grasp this, we have to start with electrostatics and understand how electrons flow, because really that's what electricity is. It's the flow of electrons. All right. Now we call it current, right? They call it current. We use words like power, wattage, which is the units for power, and those things. But it all starts with a single electric electron or electric charge. Okay. So what we're going to talk about right now is an electric charge. So when we talked about this last year, and Aaron's here from grade 11, the first thing I say about it, the first time you notice an electric charge or you get reminded of electric charge, often is when you walk across carpet and then you touch that door handle, right? You get that shock, all right? You rub your butts in these seats long enough on the plastic seats and you hit the bars on the side, you're going to get a shock. So what's happening is that charge is jumping. you provide a ground for that charge. So it exists around the doorknob, but has nowhere to go until you provide a ground for it to go through. All right, and get out of your body. Okay, so I can go through, well, basically law of electrostatics. So last year, I don't know if you recall, I had the pith ball and all of that last year. Do you remember that?
Yeah.
Okay, so I probably don't need to bring it out again. So I'll just draw it. I'll just draw it here. So you have a pith ball, you have a rod that you bring towards it, right? And if they both have the same charge, what's going to happen to the pith ball as I bring it? Right. So the first law of electrostatics says that equal charges repel each other, unlike charges attract to each other. Fair enough? Okay, so that's basically the first law of electrostatics that you have to learn. All right? So the first part of 382 and 83 is just going back through all of that stuff. Transferring electrostatic charges. So depending on what material you use, whether it's fur, silk, whether you use a rubber rod or a glass rod, that will determine whether or not you have an excess amount of electrons or a deficiency in electrons, meaning that you're short electrons in the outer level. So he explained that real well yesterday about the valence shells, right? You guys remember that?
Mhm.
How many of you, do you all take chemistry?
Yeah.
You like to take chemistry? No? Okay, do you know what valence shells are? No? All right, so you've got the nucleus of a,
Oh, I think I remember that.
okay, so you have a nucleus, you probably did in grade 10 science. You have electrons around the outside of a shell, in shells, right? And so some of them, the maximum you can have in the shell on the outside is 8. All right? So if you're full up, okay, you're then neutral. You have the same amount, 1, 2, 3, 4, 5, 6. So this one's deficient, meaning that you have more protons than you do electrons in this case. All right? So it would accept electrons into it because it's deficient of them. And then some will have more in their outer shell and they can pass them on to the other shells that are deficient in them. So that's how electrons work. All right? So by adding electrons to this, I'm making it negatively charged because most atoms, okay, are going to be, or the atoms are going to be neutral if they have the same amount of protons as they do electrons, right? So when I add electrons to it, it becomes negatively charged. When the electrons flow out of it, it becomes positively charged because you have more protons than you do electrons. Does that make sense?
Yeah, that's the one thing I sort of remember a little bit.
Okay, so that's the simple way of looking at it. So if you look at transferring electrostatic charges on page 385, it just shows you how the electron flow works. All right, so it has two good conductors. It has positively charged, it has negatively charged, and which way the electrons go. So only the electrons can flow. So protons stay as is, so the electrons can flow. So if you add electrons to where there's protons, you'll end up with a negative charge because there'll be more of them than protons. Okay? So if you have a positive charge, you add negative ones to make it a neutral charge. And then they talk about rubber rods and glass rods at the top of page 386. So I'm not going to go through this. This is going to be a reading exercise for you to start with, and then I'll get into the rest of it. Residual charge by induction. So I demonstrated last year using magnetism how residual charge works. Okay, so right now I have a nail in a paper clip. Can't pick it up. All right, now I've got a magnet here. I might need the other one. I'll take the stronger one. So we have to get used to these too, because our next section down the road, or one of our next sections down the road, is electromagnetism and how we create stronger magnets. So you can see this is a pretty strong magnet. All right, you have a North Pole and the South Pole here. So if I leave it hanging like that, the moment I bring it close, it wants to attach because of the dipoles. All right, same idea, same concept. Negative charges and positive charges are trying to bring it together. Okay, so right now, this thing can pick it up. Now how come? Because I've created magnetism. I've transferred magnetism from here into that nail, and now it's become magnetic. The same thing works when I bring a charge close to it. I can charge something by bringing it close, touching it, and then it is going to fall off. All right, eventually. So again, nail, no magnetism. Stick it on the bottom of here. Becomes magnetic, which you would expect because it basically it's a lot like an electric experiment where you've got the electrons flowing through it, becomes a conductor, and then when I remove the magnet from it, this still has magnetism on it. Okay, so it still creates the same effect that the magnet does. All right, so the same thing happens with electron flow. Once you charge something, it will stay charged. Okay? Now, some simple math behind this. Okay? A point charge. So I'm writing this down now. Again, because I went through this at the end of last year, I'll go through it quickly, but we are going to do more work with it. But you know, like we just introduced it to you. So a point charge. So basically what a point charge is anywhere you've got any static, you've got a point charge. You've got a positively charged ion, all right, somewhere in space. And around that charge, I have electric force. So around that charge, there's electric force. Call it field if you like. There's electric force around there, electric force field around that positively charged. So it just stays as is. It doesn't move. It's just hanging there. And once you bring something close to it with another charge, then once it's inside that electric field, then we see what happens to it. Okay? So right now, we have a charge Q, all right? I'm now going to bring in another positive point charge, also with an electric field around it. And as I move it closer, as I move that charge closer to this charge, what's going to happen to them? They're going to repel. So these lines are going to go like this. They're going to come closer to each other and they're going to repel each other because the two electric force fields are going to work against each other. Fair enough?
Yeah.
All right. Now, if I have two charges, I can calculate what the magnitude of that force field is. Force, again, measured in newtons is the units. I have K, which is Coulomb's constant. I'll write that out in a second. Q1, Q2 over the distance squared. So what it's saying is this, that the amount of force between two charges is proportional to the amount of charge on each one of them, each Q on both of them. Okay? So the larger you have the charges, the more force is going to be. Now, where I should be equating this to, or making it an analogy for it, is if you look at two bodies, such as like the Earth and the Moon, the larger the object is, the larger the mass, the more force you're going to have between them, right? So the larger the charges, the more force there is going to be between them. Now, if you think about the further you get away from the sun, what happens to the force of gravity the further you get away from the sun? It diminishes. It gets lower, right? Same thing happens here. The further I spread those guys apart, the greater the distance, the less force there's going to be on it. Because I'm increasing my distance, it's inversely proportional to that. Okay? Q is measured in coulombs. That's charge. Okay? Now 1 coulomb of charge. 1 coulomb of charge has 6.25 times 10 to the 18 electrons in it.
That's Coulomb's constant.
No, Coulomb's constant is the previous. Oh, what is? No, I haven't got the Coulomb's constant yet. I want you to work on this first. Okay, so 1 coulomb of charge is equivalent to 6.25 times 10 to the 18 electrons. Now think about it. When we talk about current, current is the measure of the amount of charge that passes through a circuit, a given point in the circuit, in a certain amount of time. It's the number of coulombs per second. That's what current is. Okay? But what is actually passing is not a charge through that spot. It's electrons. Everything we have in electricity is electron flow. All right? So we can also find out the charge on 1 electron. The charge on 1 electron is 1.6 times 10 to the negative 19 coulombs. So very small. The charge on 1 electron is 1.6 times 10 to the negative 19 coulombs.
Is it Coulomb's cube?
That's charge.
This is the symbol for charge,
Oh,
and the units are coulombs. C. So far, so good? Okay? Coulomb's constant is 8.93 times 10 to the 9 newtons meters squared over coulomb squared. All right. Again, this isn't new to you, right? We did it. It's a refresher. I know it's been a year, but it's a refresher. Okay. Look at the bottom of page 388. Coulomb's law of electrostatics. The force between 2 point charges is directly proportional to the product of their magnitudes and inversely proportional to the square of the distance between them. So the math jargon says this: the larger you have charge, the more force is going to be between the two. The larger you have distance, the greater the gap, the less force you're going to have. That's what that means. Okay? And that's Coulomb's law of electrostatics. So far, so good?
With larger distance and less.
The larger you have distance, the less force you're going to have.
makes sense.
Sorry, there was one other one I wanted to put on here, and it always seems to come later in the book. Just find it. I can't find it. Okay, doesn't matter. All right, so read the example. Find the force between charges plus 100 microcoulombs and minus 50 microcoulombs located 50 centimeters apart. Okay, so the first thing that you want to identify is that I don't want to work in microcoulombs. The only time I work in microcoulombs is if I'm working in capacitance. So everything else has to be changed. So instead of 100 microcoulombs, I'm going to go 100 times 10 to the negative 6 coulombs. Okay? 50 times 10 to the negative 6 coulombs. So far, so good? My distance, how far apart are they? For me? Oh, 0.5 meters, is that what you said?
Yeah.
Okay? All right, so now we just have to find the force between them. Now, notice I didn't put the signs on them. Okay? As long as I know they're plus and negative, I know that they're going to be attracted to each other. So when I write their direction, I write that they're attracted. Okay? Eventually, we'll have to get into that more. So I've got 8.93 times 10 to the 9 times 100 times 10 to the negative 6 times 50 times 10 to the negative 6 over 0.5 squared equals. Okay, use your calculators. Get used to the exponent button on your calculator again.
178.6.
Let's make sure we got that answer the same as everybody so that we know what we're doing with the calculators. Everybody okay? Yeah. So what we did last year is we started with 2-point charges, then we added a 3rd point charge in, sometimes in the middle, sometimes in a different area, and then we had to find out what the net force was on them. So that's what we'll lead to eventually. But today, just the very basics. The last thing I want to do is I want to calculate this guy now. I want to calculate, using the force, I want to calculate the intensity of the electric field around this. Okay? So I know that there's a force around this charge, this Q charge, right? So what I'm going to do is I want to calculate what we refer to as my electric field intensity. So how strong the electric field is around that 1-point charge. Okay? Now, we're going to use a second E tomorrow, but for today, to calculate the electric field intensity, I need to know the amount of force and the magnitude of the charge to get my electric field intensity. And the units for electric field intensity, newtons per coulomb. The electric field intensity at any point in the electric field is the force per unit positive charge at that point. The electric field intensity has the dimensions of Newton per coulomb.
So you know how to put the first one?
For the example, you're on page 392? Oh no, just 392. Okay? All right, so look at page 392. It says a charge of 2 microcoulombs is placed in an electric field. A charge of 2 microcoulombs placed in an electric field experiences a force of 0.08 newtons. All right? What's the electric field intensity? What do you get?
40,000.
Pretty straightforward. Okay? Any questions so far? So again, I'm just going back through the end of last year. I introduced all of this to you. Okay, we're going to continue with it. I want you just to go through, do everything again as a refresher. So the first couple of days are going to be pretty easy. Cameron, you just did this last week or 2 weeks ago, so you'll have all of the notes and everything. Okay, so we're going to just do this for the next couple of days. Have a look at page 393. Just a refresher for you guys again. So we want to calculate the charge between two spheres hanging on a string. You guys remember this from last year?
What was this, sorry? So you
Okay,
have to make the right angle.
right angle. Use your force of gravity here, right? That gives you your force of repulsion, which is what you want. Okay, you'll have an angle given to you. Remember this?
Yeah.
Okay, and then the distance will be determined by the length of the string. You'll calculate your distance. Now remember, this is only half the distance, so you have to multiply your distance by 2. So I'm just setting it up for you. I'm not going to do it. You guys, the first 3 questions, I'll deal with that. Okay? All right. What I want you to do is the first 12 questions on 392 and 393 in the Group A part, and then do the 7 problems in that Group B on 393. And that's it for today. Okay? All right, go through and work on that.
So to find the
Go ahead.
force gravity,
Yeah.
you don't know the